C# and AI Masterclass by Edgar Milvis Volume 4, Chapter 4. Now, let's talk about Chapter 4, Context and Deadlocks, ConfigureAwait, false, in libraries. Now, let's explore theoretical foundations. The ConfigureAwait, false, directive is a fundamental mechanism for ensuring the robustness and performance of asynchronous library code, particularly within the demanding ecosystem of AI application development. Its primary function is to decouple a method's continuation from the original synchronization context, a decision that carries profound implications for deadlock avoidance and thread efficiency. To understand this, we must first dissect the anatomy of an async state machine and the hidden context that governs its execution. Turning our attention to the synchronization context, the invisible conductor. When an async method is invoked, the C# compiler transforms it into a state machine. This state machine does not execute linearly. It pauses at every await keyword, yielding control back to the caller. The crucial detail lies in where the code following the await, the continuation, resumes. By default, await captures the current synchronization context or task scheduler if one is active. In UI applications, WPF, WinForms, or legacy ASP.NET, Precore, this context acts as a dedicated thread affinity model. It ensures that code resumes execution on the specific thread that owns the UI element or the HTTP request context. While essential for UI updates, which are not thread-safe, this mechanism becomes a trap when synchronous and asynchronous code interact. Consider the analogy of a single-threaded orchestra. The conductor, the UI thread, dictates the tempo. A musician, an async method, begins playing a note, an I/O operation. When the note is held, the musician signals the conductor and steps back. The conductor continues directing other sections. When the note finishes, the musician steps forward to play the next note, but they must wait for the conductor to point the baton at them specifically. They cannot play out of turn, even if they are ready. In this analogy, ConfigureAwait, true, the default, is the rule that says, wait for the conductor's specific cue. ConfigureAwait, false, is the rule that says, when the note finishes, immediately join the pool of available musicians and play the next available part, regardless of who is conducting. Now, let's talk about the deadlock mechanism, when the conductor waits for the musician. Deadlocks occur in the intersection of synchronous blocking, e.g., .result or .wait, and the default context capturing behavior. This is the context and deadlocks scenario mentioned in the chapter title. Imagine a UI application, Book 3 concepts, processing a large dataset using an AI model. The UI thread triggers a synchronous blocking call to an asynchronous library method to fetch a result. 1. The UI thread, conductor, calls getAIResponseAsync, result. This blocks the UI thread, freezing the interface. 2. Inside getAIResponseAsync, an await is encountered on a network request, e.g., calling an LLM endpoint. 3. The method captures the UI synchronization context. 4. The network request is sent, and the method yields control back to the UI thread. 5. The UI thread is currently blocked at .result, waiting for the task to complete. 6. Eventually, the network response arrives. The task completes. 7. The continuation, the code after the await, is scheduled to run on the captured context, the UI thread. 8. The deadlock, the UI thread is blocked waiting for the task to finish. The task is finished, but its continuation is waiting for the UI thread to become available to execute it. The UI thread will never become available because it is blocked waiting for the task. This is a circular dependency. The conductor is waiting for the musician to finish the piece, but the musician is waiting for the conductor to wave the baton so they can start the final movement. Both are frozen. Turning our attention to ConfigureAwait, false, breaking the chain. Applying ConfigureAwait, false, to the library method fundamentally alters the resumption logic. It instructs the state machine, do not capture the current synchronization context. When the awaited task completes, schedule the continuation on the default thread pool. Returning to the orchestra analogy, ConfigureAwait, false, allows the musician to finish their note and, instead of looking at the conductor, immediately look at the sheet music for the next bar. If the next bar requires immediate playing, they do so on whatever thread is currently available, the thread pool, without waiting for the conductor's specific cue. Why is this critical for AI pipelines? In AI applications, we frequently build pipelines that mix I/O-bound operations, API calls, database lookups, with CPU-bound operations, tokenization, JSON parsing, tensor manipulation. These pipelines are often reusable components, libraries, intended to be consumed by various host applications, desktop UIs, web servers, ASP.NET, or background services. If a library method awaits a network call but defaults to ConfigureAwait true, it implicitly assumes it is running in a context that supports resumption. If that library is consumed by a synchronous ASP.NET controller, precore, or a UI thread that blocks on the result, the application hangs. By using ConfigureAwait false in library code, we guarantee that the library is context agnostic. It does not care if it was called from a UI thread, a thread pool thread, or a specific ASP.NET request context. It releases the thread back to the pool during I/O waits and picks up a thread pool thread upon completion. This decoupling is the cornerstone of writing deadlock-free reusable asynchronous components. Moving on to the performance implication, context switching overhead. Beyond deadlock avoidance, ConfigureAwait false offers a performance advantage by reducing context switching overhead. In the default configuration, true, the continuation must marshal back to the original synchronization context. In a UI app, this involves queuing a work item to the UI message loop. In legacy ASP.NET, it involves returning to the specific request context. This marshalling is not free, it involves thread affinity management and queuing logic. When ConfigureAwait false is used, the continuation runs on any available thread pool thread. The thread pool is highly optimized for distributing work across available cores. By avoiding the affinity constraint, the runtime has more flexibility in scheduling the continuation, potentially leading to better throughput in high-load scenarios, such as processing streams of AI tokens. This diagram contrasts how a UI thread's asynchronous method continuation is handled, showing that without ConfigureAwait false, the continuation is forced back onto the original UI thread, potentially causing a bottleneck, whereas using ConfigureAwait false allows the runtime to schedule the continuation on any available thread for improved throughput. Now, let's talk about architectural implications for AI components. In the context of building asynchronous AI pipelines, Book 4, the application of ConfigureAwait false is a strategic architectural decision. Consider a streaming LLM client class responsible for handling server-sent events, SSE, from a large language model. This class is likely a reusable library component. 1. The interface contract. As discussed in previous chapters regarding interfaces for swapping models, e.g., OpenAI versus Local Llama, the asynchronous methods of these interfaces must be implementation agnostic. If the stream completion async method in the OpenAI implementation uses await without ConfigureAwait false, it imposes a hidden constraint on the consumer. You cannot call this method synchronously from a UI thread. 2. The pipeline architecture. An AI pipeline might look like this: input-tokenizer-network call-response parser-UI output. The tokenizer and parser might be CPU-bound, though often async versions exist for large payloads. The network call is strictly I/O bound. If the library components, tokenizer, network, parser, are written with ConfigureAwait true, the entire pipeline inherits the synchronization context of the caller. If the caller is a UI thread processing a stream of tokens, the pipeline will constantly marshal back to the UI thread for every token. This creates a ping-pong effect of thread switching, degrading performance. If the library uses ConfigureAwait false, the pipeline runs efficiently on the thread pool during the I/O and CPU bursts, and only marshals back to the UI context when explicitly required, e.g., updating a UI control at the very end. Now, let's talk about the what-if edge cases and modern considerations. While ConfigureAwait false is the gold standard for library code, there are nuances. What if the continuation needs the context? In library code, the answer should almost always be, it shouldn't. Library code is infrastructure. It should not be updating UI controls or accessing HTTP context, current, in legacy ASP.NET. If a library method needs to access context-specific data, it should receive that data as a parameter or have the context passed in explicitly, rather than relying on ambient context capture. What about ASP.NET Core? ASP.NET Core removed the synchronization context. Consequently, await in ASP.NET Core naturally behaves like ConfigureAwait false, it does not capture a context. However, libraries must still support older frameworks, like .NET Framework with legacy ASP.NET or WPF. Therefore, applying ConfigureAwait false remains a best practice for maximum compatibility and forward compatibility. The ConfigureAwait method signature. In modern C#, .NET 5+, ConfigureAwait accepts a Boolean continuon captured context. However, it also has an overload accepting a ConfigureAwait options enum. This allows for more granular control, such as ConfigureAwait options.suppress throwing, which prevents the await from rethrowing exceptions on the original context, useful in specific cleanup scenarios. Now, let's explore theoretical foundations. The theoretical foundation of ConfigureAwait, false, rests on the separation of concerns between execution context and execution logic. 1. Execution context, where, by default, async methods are coupled to the context in which they are invoked. This coupling provides safety for stateful environments, like UI, but introduces fragility when blocking is introduced. 2. Execution logic, the logic of an asynchronous operation, e.g., fetch this JSON, parse it, return the object, is independent of the thread on which it runs. ConfigureAwait, false, enforces the decoupling of these two concerns. It asserts that the library code is stateless regarding the execution context. This allows the library to be a good citizen in any host environment, preventing deadlocks caused by circular thread dependencies and optimizing performance by leveraging the thread pool scheduling flexibility. For AI applications, where pipelines are complex, often involve high-throughput I/O, streaming tokens, and must be reusable across different UI and web backends, mastering this concept is not optional, it is a prerequisite for stability. It ensures that an AI service component designed for a high-performance web API can be safely integrated into a responsive desktop agent without causing the entire application to freeze. Let's discuss basic code example. Here is the Hello World level code example for using ConfigureAwait, false, in library code to prevent deadlocks. Here, we're bringing in the necessary namespaces for our C# application. System provides fundamental classes and base types, while system, threading, tasks is absolutely crucial for asynchronous programming in .NET. This namespace gives us access to task and task tier result, which are the cornerstones of the async/await pattern. We're also defining a class library service which will encapsulate some reusable business logic, acting as a component in our system. Inside library service, we define fetchDataAsync. Notice the async keyword at line 8. This signals to the C# compiler that this method can contain await expressions, allowing it to perform operations without blocking the calling thread. At line 11, we introduce await task, delay, 100. This simulates an I/O bound operation, like a network call or database query, which takes some time to complete. The await keyword here is key, it suspends the execution of fetchDataAsync for 100 milliseconds, returning control to the caller, and then resumes when the delay is over. This is fundamental for keeping applications responsive. Now, let's look closely at lines 14 to 17. Here we have await task, delay, 100, .ConfigureAwait, false. This is a critical point for understanding asynchronous programming in .NET, especially when dealing with synchronization contexts. When you await a task by default, the runtime captures the current synchronization context, if one exists, like a UI thread context or an ASP.NET request context. After the awaited operation completes, it attempts to resume the method on that same captured context. This is often desirable in UI applications to avoid cross-thread UI updates. However, in library code or backend services, this can lead to performance overhead or even deadlocks if the captured context is blocked waiting for the async operation to complete. By calling ConfigureAwait, false, we explicitly tell the runtime, I don't care about the original context, just resume this method on any available thread pool thread. This is a best practice for library methods to prevent potential deadlocks and improve performance, as it avoids the overhead of marshalling the continuation back to a specific context. It makes the method more context agnostic and efficient. Here at line 24, we define our program class, which serves as the entry point for our console application. The main method, defined at line 26, is where execution begins. I want you to pay close attention to the comment at lines 27 to 28. It highlights a crucial distinction. In a real-world UI application, like WPF or WinForms, or a web application, like ASP.NET Core, this main method wouldn't directly call our async logic. Instead, an event handler or a controller action would. For this console demo, we're intentionally setting up a scenario that can demonstrate the potential pitfalls of mixing synchronous and asynchronous code, specifically the blocking behavior that can lead to deadlocks. At line 29, we start our main method. We print a message to the console to indicate the application's start. Now, look at lines 32 to 33, especially new library service, .fetchDataAsync, .getResult. This is a very important line for understanding potential deadlocks. We are creating an instance of library service and calling its fetchDataAsync method. However, instead of awaiting the task returned by fetchDataAsync, we are immediately calling .getResult on it. This is a synchronous blocking call. GetResult will block the current thread, in this case, the main thread, until the fetchDataAsync task completes. This is generally an anti-pattern when you have an asynchronous method and you are in a context that could await it. This blocking can lead to deadlocks, especially in UI or ASP.NET contexts where the synchronization context is captured. The warning at lines 34 to 36 is extremely important. When getResult is called, the current thread, our main thread, is completely blocked. If fetchDataAsync were to capture the synchronization context of this main thread, which it would if we hadn't used ConfigureAwait, false, inside fetchDataAsync, and then try to resume its continuation on that same blocked main thread, we would have a classic deadlock. The main thread is waiting for fetchDataAsync to complete, but fetchDataAsync can't complete because it's waiting for the main thread to become free to resume its work. Because we did use ConfigureAwait, false, in fetchDataAsync, this specific example avoids the deadlock, but it still demonstrates the blocking nature of .getResult. Finally, at lines 38 to 39, we print the result and a message indicating the application has finished, showing that even with blocking, the operation eventually completes in this specific scenario due to ConfigureAwait, false. By scanning this code you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. This lesson is excerpted from Volume 4, Chapter 4 of the C# and AI Masterclass ebook series and from the volume Asynchronous AI Pipelines. Async/await, parallelism, and streaming LLM responses. You can find all source code here, https://github.com/edgarmilvis/C# programming series. The ebook includes 20 chapters, each one with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. Thank you for your attention. I look forward to seeing you in the next lesson.